Good evening everyone, myself Gautam Sharma. I welcome you all in a Sapience Education. Now today I am going to discuss about the dual nature of the radiation and matter, and this is our part 2 video. For rest of the video you can visit our YouTube channel. So today I am going to discuss about the photoelectric effect. Today, what is photoelectric effect? As discussed, phenomena of emission of electron from the surface of the metal when radiation of the suitable frequency fall on it is called photoelectric effect, and the emitted electron is called the photoelectrons. Now let us understood the scenario. Let us consider this is the metallic plate, right? This is the metallic plate, and it has, you know, that in any metal you will find lots of electrons which are moving around it. So this is an atom and this is an electron. So electron will be present in the outermost orbit, right? Now what will happen if any energy will fall? So what will happen? Let us consider a radiation will happen on the surface. So radiation means some sort of energy will fall on this. So what will happen, the outermost it in our outermost orbit there is an electron, right? An electron will gain energy, and as soon as electron will gain the energy, so it will try to emitted out like this, right? So this is known as photoelectron. Why photoelectron? Because see, photo means light. So whenever electron will jump out from its surface, when you give a light on or a radiation on the surface of the metal, then this is considered as a photoelectron, and the current so produced is called photoelectric current. So let us consider there is a metallic place like this, and this is your uh, there is two metallic plate like this, got it? And you know that this is an axis of electron and this is a negative, means positive charge. So what will happen, as soon as light will fall on this, so what will happen, electron will gain some sort of energy, right? Gain energy. And when it will gain the energy, then what will happen, electron will come out from this and it will start moving toward the positive, and this will current will start moving. So this is considered as a photoelectric current. Now alkali metal like lithium, sodium, etc. shows a photoelectric effect with the visible light. So alkali metal, if the metals are sodium, so what will happen? It will eject the electron with the color visible light, and the metal like zinc, cadmium, etc. are sensitive only to the ultraviolet light. So I hope you have understood this. Now see. Now from this question you will able to understand what they are asking. So before doing this question, so we should go ahead for some sort of topic. Now what is matter wave? Wave theory of electromagnetic radiation explains the phenomena of interference, diffraction and polarization. So in earlier classes, so wave or light, we have considered light as a wave, and from this light wave we have come to arrived in the conclusion about the interference diffraction pattern. We have seen the diffraction pattern like this, right? Diffraction pattern like this, and as soon as we have also seen the interference pattern like this. So interference was, you have seen the interference pattern, polarization of the light, sorry. On the other hand, quantum theory of the electromagnetic radiation successfully explained that photoelectric effect. That is, we have just now done about the photoelectric effect, quantum effect, black body radiation, X-rays and spectra. From photoelectric and quantum effect, it is clear that the particles, photons of a radiation is colliding against the another particle. It means that whenever you see or observe that photoelectric effect, from here we can say that it is behaving as a particle. It is behaving as a particle. But when we discuss about the diffraction and interference pattern or the polarization, so what we observe? We can observe that this is wave nature, right? So it is due to this reason that it could concluded that the photoelectric effect and quantum effect of the radiation possess a particle nature, right? It means that radiation of sometimes behave as a wave and sometimes as a particle. Therefore, Louis Vector de Broglie suggested that the particle like electrons, protons and neutrons etc. have a dual nature. and they have a particle as well as wave nature. So it will behave sometimes as a wave, as well as you can understood that it will behave as a particle nature. So that's why it is considered as a dual nature of the matter. Now, wave nature of the particle. De Broglie hypothesis. According to the De Broglie, a wave is associated with the moving material particle which controls the particle in every aspects. The wave associated with the moving material particle is called the matter wave de Broglie. So whenever we are thinking about the wave, matter wave, so what we need to understand that matter wave has some sort of a relation, that is lambda is equal to h by mv. So this is called the de Broglie wavelength, where m and v are the mass as well as velocity of the particle and h is the Planck constant. Now, as per the Planck's quantum theory, the energy E is equal to h, that is Planck constant, into frequency. So mu, basically nu is your frequency and v is your velocity. So from here, v is velocity. Now nu frequency can be written as hc by lambda. So from here we have got one conclusion that energy can be written as energy E is equal to hc by lambda. Now one more important derivation has come that is given by Einstein theory, that is E is equal to mc square. Now from this equation 1 and 2, we can say that lambda is equal to h by mc, or lambda is equal to h by p. Now if a material of the particle having a mass m moving with the velocity v, then the momentum of the particle will be how much? P is equal to mv. So this is the basic definition for the momentum, right? So this is velocity. Now lambda is equal to h by mc. C is basically considered as a velocity only, so mv we can write, but mv is considered as the momentum, so we can write h by momentum is equal to lambda. So this is one of the important relation, and this can be considered as a de Broglie wavelength. De Broglie wavelength. I hope you have understood this. Now let us consider now, as we have got this show, from this we can conclude that de Broglie wavelength, that is lambda, is inversely proportional to the velocity of the particle. So as move faster than the wavelength, so it will have, now from here we can understood that lambda, that is wavelength, is inversely proportional to the velocity v. So it has move faster, so wavelength will be smaller. So if it will move very fast, so what will happen? Lambda will decrease. Now if the particle is at rest, that is velocity is equal to 0, so lambda is equal to infinity. Such a wave can, so if lambda is equal to infinity, so such a wave cannot be visualized. So de Broglie wave cannot be electromagnetic in a nature, because electromagnetic wave are produced by the motion of the charged particle. Yeah, very important. Electromagnetic waves are produced by the motion of the charged particle, but here in de Broglie wavelength, what we required, we don't require any charged particle. That's why both cannot be the same, right? Now the wavelength of the wave associated with the moving particle defines a region of uncertainty within which the whereabouts of the particle are unknown. What do you mean by this? So the wavelength of wave associated with the moving particle of a definite range of uncertainty within which the whereabouts of the particle are unknown. The fact that the Heisenberg uncertainty principle came out, and according to this, what happened? It is not possible to measure both the position. See, very important. It is never be possible that you will able to find either position or either velocity. It is not possible to measure both position as well as momentum. So if momentum is there and the position is there, so what will happen? If one of the things are known, then other thing cannot be known. And if position is known, so you cannot tell that momentum is known. This is always some uncertainty. Uncertainty means if momentum is unknown, known, then we cannot specify its position. Why? Because its velocity is there. But if we specify the position, then momentum will be uncertain, right? So this is called the Heisenberg's uncertainty principle. That is why h is equal to h plus is equal to h by 2 pi is given. But you know that mm, product of delta x into delta p is equal to h by 2 pi, where it has been considered that if this is okay, then this will be not okay, and if this is not okay, then this will be okay, right? So I hope you have understood this. So if one of the things are certain, then other thing that definitely it won't be the certain, right? So I hope you have understood. Now, common features of the matter waves are, some of the common features of the matter waves are given below. Matter wave can travel in a vacuum, and hence they are not mechanical. Matter wave are probability waves, that is amplitude of the which of the probability of existence of the particle at that point of the amplitude of a wave A, and then probability of the particle being found in a small volume is around like this. So if see, let us consider if the wave has a amplitude of A, wave has a amplitude of A, and the volume, let us consider volume around which it will be observed will be dV. So what we can say that the probability of getting the wave is equal to how, what is the probability of getting wave is equal to A square into dV, right? A square into dV. So I hope you have understood this. Now let us solve one of the problems so that you will able to understood the fact that what they are asking. Now let us consider there is a question, a monochromatic light, that is single wavelength. Light of a wavelength of this nanometer is provided by the helium neon laser. The power emitted is 9.4 megawatt. Find the energy and the momentum of each of the photon. So what you need to do for finding energy? So first of all, they have provided you lambda, right? And they have also provided you the power, right? That is equal to 9.242 watt, milliwatt. So that is equal to 9.42 into 10 to the power minus 3 watt, and lambda is equal to 632.8 into 10 to the power minus 9 meter. They have provided we, right? Now what do we need to do? We need to find energy. So energy is equal to hc by lambda, we have done. So h is the Planck constant, so you need to put the value of Planck constant like this, and 10 to the power minus 34 into 3 into 10 to the power 8, and divided by 632.8 into 10 to the power minus 9. So I hope you will get this as a 3.14 into 10 to the power minus 19 joule. So this is the way how to proceed for the problems, right? Now, how many photons per second arrived at that C? So in this way, you will able to solve all the problems related to this. So basically, you need to go through all the formula, and you need to solve the problems, right? How fast does the hydrogen atom have to travel in order to have the same momentum as that of the photon? So you need to find basically velocity v. So E is equal to h by momentum, that is equal to h by m into velocity. So from here you can find E is given, h is the Planck constant, and they are asking about they have given, see, they are asking about, they are asking about see, they are asking about the velocity. So you need to put the value of the mass. So which mass you need to put here? See how many see how fast hydrogen atom. So you need to put the mass of the hydrogen atom, right? Right, to travel in order to have a same momentum. So you need to put the mass of the hydrogen atom, then from there you will able to find the velocity. So I hope you have enjoyed the session. Thank you for watching my video, and I will come up with the next, so try to be connected here. Thank you.